Now, welcome back to our acids and bases section, and I just left you with a few questions at the end of last class to take a look at in terms of conjugate acid, conjugate base, and then the conjugate acid base pairs. Okay, I'm going to run through the answers very quickly with you now, just to make sure you've got the grip with what we were dealing with in previous classes. But just to recap very quickly, we've got two theories in terms of acids and bases, okay, and those two theories are an attempt to describe what an acid and a base actually is, okay. Up to that, we had a junior cert understanding that acids were sour, acid had a pH of less than 7, and so on. Okay, acids are sometimes strong, sometimes weak, and sometimes dilute, and sometimes concentrated. So again, those four words, I'll revise them with you in a few moments. And likewise for bases. Bases have a pH of greater than 7, bases have a soapy feel, bases turn litmus paper blue, and acids turn litmus paper red. Okay, so you've got all these things coming from junior cert that we know, but we're delving into what the nature of an acid and a base actually is. And there are two theories. The Arrhenius theory, which says that an acid is any substance that once put in water or in aqueous solution produces H plus ions. Arrhenius also says a base is any substance when placed into water produces OH minus ions. But it's restrictive on two accounts. Number one, it says acids and bases can only be acids and bases and undergo dissociation in water. We know that's not quite true. Okay, and number two, it only says that it can happen in an aqueous medium. Sometimes it can happen in the air. So that's the second place where it doesn't work. So then it was expanded onto looking at what the H plus ion actually was, and we discovered that H plus ion was a proton. So Bronsted and Lowry, more or less at the same time, came up with their definitions of what an acid and a base was, and their findings resulted in two new definitions. An acid is a proton donor and a base is a proton acceptor. And what that did was it opened up the nature of substances to being acidic and basic that were never considered to be of that nature before. So water, for example, was always considered to be just neutral. However, under Bronsted-Lowry theory, it can act as an acid or a base. And that's why we call it an amphoteric substance, okay? And then we've also discovered that there are acid-bases reactions going on all the time, even between two acids. Or they can happen in the gaseous phase. So thanks to Bronsted and Lowry, the definitions are an acid is a proton donor and a base is a proton acceptor. And then we discovered that in order to transfer a proton, it has to be a simultaneous process of give and take. So that means that acids and bases work in pairs. And if the proton is donated going forward, well, then it can be donated going backwards. So we end up with reversible reactions. And in a reversible reaction, not only will you have an acid and a base, but you'll also have a conjugate acid and a conjugate base. Because if the reaction is taken going backwards, well, then the proton is simply given back. So if the forward reaction is like this, acid, base. And if the backward reaction is like this, conjugate acid, conjugate base. Okay, and that's what the questions I left you with the last day simply wanted to go through with you. So let's take a look at these ones here. Write down the conjugate base. Now, if you're to write down the conjugate base, that means that all of these starting points are acids. Okay, so if you want to get the conjugate base, you're going to start with the acid. So if all of these are acids, well, then under Bronsted-Lowry theory, what do acids do? They donate protons. So in order to get the conjugate base, we simply write down what this would be if it loses a proton. So if I take CH3, COOH, and remove a H plus, the first thing that's going to happen is that the H is going to disappear. CH3, COO. And because I'm removing a plus proton, I'm going to have a negative left over. So the answer to the first one is CH3, COO minus. Okay? HS minus. Now again, look, HS minus. If I lose a proton or donate a proton, first of all, that hydrogen will go, leaving me with S, but the amount of negatives will increase by 1. So you get S2 minus. NH3, again, NH3 minus or donates a proton. What does it become? Well, first of all, it becomes NH2 because it's lost a proton with a negative charge. So NH2 minus, and so on, so forth for the rest of them. So allow me to do this quite quickly. H2O, when it loses a proton, will become OH minus. HCO3, when it loses a proton, will become CO3 with a double negative. NH4 when it loses a proton. Now be careful here, look. NH4 plus. When it loses a proton or donates a proton, will become NH3, but the plus charge that was on the original molecule has also gone. So it leaves you with neutral ammonia, NH3, and that's what you've got to be careful with. Next one, H2NO3. If you remove a H and a plus, what are you left with? HNO3. See? OH minus. Now again, you're removing a H, so you're left with O, and you're increasing the number of negatives to 2. And lastly, CH3, NH3 plus. Now, people say, well, where am I going to remove the hydrogen there? Well, obviously it's from the end. So it donates a proton, meaning it becomes CH3, NH2. And a plus goes with it as well. So first of all, CH3, NH2. So it loses the hydrogen, but it also loses the plus and leaves it neutral. So they are all the conjugate bases of the linked acid that we began with. And then I asked you in the second question to do the opposite. Write down the conjugate acid of each of the following Bronsted-Lowry bases. So you're starting with a base. Now, under Bronsted-Lowry theory, what does a base do? It accepts a proton. So they pick up H+. Okay, every single one of these. So all you're doing is adding H+ onto each of these molecules. So let's do the first one. NH3, when you add on a H+, will become NH4+. Okay, so you just bring the number of hydrogens up by 1, and then you add on the positive charge as well. Next one, HSO4 plus H+, so it's accepting a proton, brings the number of hydrogens up to 2. Now, what does a plus do to a minus? Cancels. A plus to a minus cancels, so therefore there's no charge left on my resulting conjugate acid. SO4 2 minus, add on a proton. What does that become? HSO4, and 1 plus cancels 1 minus and leaves 1 minus behind. So the charges are extremely important. OH minus plus H plus, same thing again. Number of hydrogens up to 2. The plus cancels the minus, you end up with water. CO3 2 minus, add on your H, so H plus H plus, add on your H, CO3, and the plus cancels one of these negatives and leaves 1 behind. If I add on a H plus here, H2CO3, and the positive and negative cancel. HS minus with a H plus gives H2S, and again the charges cancel. H2PO4 minus. Why? Because when I add on H plus, bring the hydrogens up by 1, and 1 positive cancels 1 negative, leaving 1 negative behind. Next one, proton acceptor, HClO4, and the charges cancel. Next one is HS minus, and finally, now be careful here, if you've got HF and you're accepting a proton, your hydrogens go up to 2, and the positive charge always goes over the molecule as well. So H2F+. Now it's important that you understand how to write down conjugate acids and conjugate bases if you're given the corresponding acid or base. Okay, and just remember, if they ask you for a conjugate acid, you're starting off as a base, so you're going to accept protons. If they're asking you for the conjugate acid, then you're starting off as a base. Sorry, if they ask for a conjugate acid, you're starting off as a base, you're going to accept protons. If they ask you for a conjugate base, then you start off as an acid and you donate protons. And watch the charges very carefully. The more protons you donate, the more negative you become. The more protons you accept, the more positive you become. Simple as that. And lastly then, I asked you, and we went through this already, to work out the acid-base pairs, work out the acid-base pairs in each one of these particular reactions. Now I'm going to go through this quite quickly just so you can check your answers. Maybe the first 2 or 3 I'll do in terms of explaining it to you, and then you can just follow the answers yourselves for the rest of them. So let's take the first one. Notice which of the species on the right hand side has increased by a hydrogen. this one here, HNO3, has become H2. So it's plain to see that we have moved a proton that way. From here, the acid, to there, the base. Okay, now, in the backward reaction, because this species here has picked up an electron, it'll send it back. So therefore, this one is the conjugate acid, and this one is the conjugate base. Meaning that you have a base with a conjugate acid as pair number 1, and you have an acid with a conjugate base as pair number 2. Okay, next one. Both species starting off, how do they change? The CH3COOH becomes CH3COOH2. So therefore, it has moved this way. See that? Meaning that's the acid, that's the base. In the backward reaction, this species here will give back the electron over there, meaning that's the conjugate acid and that's the conjugate base. So where are my pairs? The acid with the conjugate base and the base with the conjugate acid. Okay, so that's it there. Next one, HNO3 becomes NO3. So that's lost it. So that has caused its electron to go this way, from the acid to the base, meaning that the electron on the backward reaction will go the other way. Conjugate acid, conjugate base. So where are my pairs? The acid with the conjugate base and the base with the conjugate acid. Okay, now let's speed up the process. So in this situation, part D, we see that this species has picked up an electron, which means an electron has moved from the acid to the base, and therefore will move back from the conjugate acid to the conjugate base. And where are your pairs? The base with the conjugate acid and the acid with the conjugate base. Okay, this one, acid, base, conjugate acid, conjugate base. Okay, and you can see your pairs again, the acid with the conjugate base and the base with the conjugate acid. Next one, that's the acid, that's the base. This one here, having picked up the proton, is the conjugate acid and the conjugate base. So acids with conjugate bases and bases with conjugate acids. HSO3 minus and H2O, look at what happens. H2O becomes H3O. So the proton is given this way, from H2SO3 minus to H2O. Acid, base, conjugate acid, conjugate base. Next one, H3PO4 becomes H2PO4. So that's the acid, that's the base, that's the conjugate acid, and that's the conjugate base. The second last one, NH4 plus and CO2 has become NH3 and HCO3. So again, the acid, the base, the conjugate acid, the conjugate base. And finally, H2SO4 and nitric acid. Now we had this one kind of already, and we noticed that the HNO3 goes up to H2NO3. So therefore that happens to be the acid. If I can get in here, that's the acid, that's the base, that's the conjugate acid, and that's the conjugate base. Now it's vitally important that you know how to do those. Absolutely vital. Okay. If you have any difficulty with any of those, do come back to me with an email and I'll see if I can get round to going through them with you again. To finish this section, and we're finished now, so we are going to have a test on this very, very shortly. I'll tell you when. But just to finish this section, just a quick word on what we call neutralization. Now, as we already know from junior cert, neutralization is the chemical process that takes place when an acid and a base meet and form water. Okay, now put that another way. When an acid of less than pH 7 comes together with a base of greater than pH 7 and give you a resulting solution of pH 7. Okay, but that's what we learned at junior cert. It's not the full story, because when you neutralize something, an acid and a base comes together like this. There's your acid, there's your base, to give you, yes, the water that we expect, but it also gives you salt. Okay, now the salt doesn't have an effect on the pH per se. So this might be, say, for example, pH 2. Okay, this one here might be pH 12. This one here will be pH 7. Why? Well, think about this. What's 2 and 12? If you add both of those together and get the average, what do you end up with? 14 over 2, which is 7. So that's why acids and bases neutralize one another. Okay, but more importantly than that, we need now to think of these in terms of what's going on with the H plus and the OH minus. And in order to do that, let's just take a view and a journey through this. So there's your acid, there's your base, there's your water, and there's your salt. And that is the definition for neutralization. Neutralization is the process by which an acid and a base react together to give us salt and water. That's the definition, and it's the definition I'd ask you to remember. All right. Because we've started to look into acids and bases, we now know from Bronsted-Lowry that an acid is a proton donor and a base is a proton acceptor. So what's neutralization in terms of that situation? Well, in that situation, we're talking about the acids H plus and the bases OH minus. Okay, so more or less going back to look at Arrhenius rather than looking at Bronsted-Lowry. Because if you take H plus from the acid and it finds itself an OH minus, what's going to happen? The number of hydrogens will go up to 2 and the positive and negative charges will cancel and they will leave you with required water. So to get the water formed, the H plus from the acid and the OH minus from the base must meet in the same system. So in all neutralization reactions, the metal of the base will replace the hydrogen of the acid. For example, if you add HCl with NaOH, now what I would suggest you do here is the following. Whenever you're given a neutralization reaction like that, look at the two species that they give you and ask yourself, how do I form water? And I form water by taking the OH from the base and the H from the acid. So they will go away, both of them, and they will form your water. Okay? Now, what will the Na and Cl do? Well, whilst there's water present, nothing. But when you drive the water off, both of these things will react and give you the salt, which is the NaCl. So the easiest way to think about this is as follows. When you take an acid and a base together, take the OH and the H together to form water, and the remnants of the acid and the base will come together to form the salt. Okay, as in the situation there. What about this one? MgOH2 plus HNO3 gives MgNO3 twice and H2O. Now here's what I would suggest. Watch carefully. The hydrogen and the OH are needed to form water. There we go. Now what's left? Mg and NO3. Now when we take the Mg with the NO3, this is where our radicals are extremely important, because the valency of magnesium is 2, being in group 2, and the valency of the nitrate radical is 1. So therefore, when you cross these over, you get Mg1 NO3 twice, and that's why it's written that way. Okay, so the best thing to do is to basically always, when you've got an acid-base reaction, take the hydrogen and the OH out of the equation to form water, and then bring the magnesium and the nitrate in this case here, or the chlorine and sodium, or whatever the remnants are of the acid and the base, bring them together. So where do we have neutralization happening in everyday life? Well, medicine. You get a touch of the old indigestion. Every one of us know it after Christmas. Too much turkey, too much stuffing, too much roast potatoes, and you sit back on Christmas evening with a pain in your stomach instead of enjoying television. And it's basically an overproduction of acid. So what the acid does is it crawls up your esophagus, okay? Now, your esophagus only has nerves about halfway up. So the acid doesn't affect your esophagus down here. When it starts to crawl up behind your heart, you begin to get this kind of a burning sensation. The acid is actually burning the nerves in your esophagus. And you know that you need a spoonful of some type of, be it bicarbonate of soda, or Rennies, or Tums, or Settlers, or any of those things that get rid of acid. That's a neutralization reaction. You take a base, calcium hydroxide, or not calcium hydroxide, calcium carbonate, you take a base and it neutralizes the acid. Okay, so that's one place we use everyday neutralization. Another place we use it is in agriculture, land, in farming. If it's found that the pH of the soil is too low, that it's in the acidic area, and plants don't thrive in that, well then what we do is we can add lime. And lime is calcium hydroxide. And when you add lime to the soil, it neutralizes the acid and brings the pH upwards to make the soil far better for cultivating crops. Another place is environmental protection. So for example, we've all had a problem for many, many years now of acid rain. Acid rain gives rise to acid lakes. Okay, so the pH in your water, the water in your lakes begins to drop, and the life in and around that can't thrive and sometimes starts to die. So to bring the pH back up again and to neutralize the acidity in the lakes that's come from the air, we use limestone. And limestone is scattered in a body of water to bring the pH up. And finally then, as we spoke about already, toothpaste, which is a base, is used to neutralize the acid in your mouth to stop cavities. Baking soda is wiped on bee stings because baking soda is a base and bee stings are acidic. Vinegar is used on a wasp sting because wasp stings are basic. And finally then, conditioner on shampoo. Very few people know this, but shampoo is acidic. Okay, I should say, sorry, shampoo is basic. And what the shampoo does, if you put it into your hair, is it causes your hair to have more or less the same charge. So your hair gets frizzy, all right? If you use just shampoo, your hair gets frizzy. What does the conditioner do? It neutralizes the effect of the shampoo so that you don't get that frizziness in your hair. So shampoo and conditioner is chemistry. It's the action of the conditioner on the shampoo to stop your hair from becoming frizzy. And believe it or believe it not, it is an acid-base reaction. Okay, so, and they will ask you for some of those. Where do we have neutralization in everyday life? There's loads of examples, and I've given you those 2 slides, so all you've got to do is to learn them. Now, to finish this thing with strong acids and bases, strong and weak, and we've dealt with this. Look, there are 4 words. There is strong, there's weak, there's concentrated, and there's dilute. Okay, strong and weak refer simply to the amount of H plus ions I can produce, or the amount of protons I can donate. Okay, if I can donate a lot of protons, then I'm going to be a strong acid. If I donate very, very few protons, I'm going to be a weak acid. But the terms concentrated and dilute have only got to do with how much water you're using. So if you use a little amount of water, the acid will be concentrated, and if you use a lot of water, it'll be dilute. So therefore, it is possible to have 4 situations. You can have a strong concentrated solution. You can have a strong dilute solution. You can have a weak concentrated solution, and you can have weak and dilute. Because once an acid is weak, it'll always be weak. What happens between these two is that the acid has different amounts of water. This one is a bad proton donor with no water or very little water. This one is a bad proton donor with a lot of water. Good proton donor with little water, good proton donor with a lot of water. Okay, so just keep that in mind, that strong and weak are not the same as concentrated and dilute. They are very different, and you do need to know the difference between them. So there's a table of the acids that are strong and the bases that are strong, and then the acids that are weak and the bases that are weak. And you need to learn this. These are the acids and bases that are going to haunt you for the rest of this course. Obviously, sulfuric acid. Here, hydrochloric. Here, nitric. They are the 3 strong, what we call bench acids that we use in the lab. This one is called ethanoic acid. Ethanoic, ethanoic acid. Better known as the active ingredient in vinegar. Okay, this one, phosphoric acid, also present in fizzy drinks. And this one here, methanoic acid, which is in the stings of ants. Sting, S-T-I-N-G, stings of ants. So because these little ants are tiny, they produce little molecules. Okay, so HCEOH is methanoic acid, which is found in the stings of ants and also in nettles. So next time you get stung by a nettle or an ant, it's an acid. Get an old dock leaf, big leaf, break it open, little white liquid inside, rub it on, neutralization, pain is gone. What about the strong bases? Sodium hydroxide, Okay, potassium hydroxide. Calcium hydroxide. So they're kind of boring. They have the same surnames, every one of them. And finally, my weak acids are ammonia, which is NH3, and sodium carbonate, which we will be using very, very shortly, please God, on our return to school, in making up a solution of a known concentration. Now, that table, that's a table you have to know. So now that we're finished this chapter, I need you to revise it. There is going to be a test on this chapter very, very shortly, and that table will be asked. It'll be asked in terms of what the name is, whether it's strong or weak, and so on. So please make sure that you learn that table. That's that chapter finished. That chapter is done. Okay, there's very little we can actually examine except for the fact that you understand in acids and bases the Arrhenius theory, the Bronsted-Lowry theory, the conjugate acid-base pairs, and then finally, as we said already, what is neutralization and where does it occur in everyday life. Okay, so relatively short class today. That's it. I want you to revise those slides. We will have a live class on Friday just to make sure that everybody is okay with the slides and with the videos and so on. You may have questions you want to ask. Gather them now and fire them at me on Wednesday. Or sorry, on Friday, not Wednesday, Friday. Today is Wednesday. Friday. Okay, thanks.